Welcome everyone. In today's video, I'll be covering the Mozilla article titled A Crash Course in Memory Management by Lin Clark. I posted the link in the description section, so if you want to look at it after watching this video, feel free to do this. This is the first time I'm looking at this article, so I'm new to this article also. So if you're watching this video, you'll be learning along with me, I guess. I don't know everything about JavaScript, so it'll be a big learning experience for me. This is part one in a three-part series of articles that Lin wrote. So I'll be covering all three of them. So today I'll be just covering the first one. So the article starts out by saying, to understand why array buffer and shared buffer were added to JavaScript, you need to understand a bit about memory management. Array buffer and shared array buffer were added to JavaScript standard. So to understand why they were added, we need to understand a little bit about memory management. So you can think of memory in a machine as a bunch of boxes. I think of these like the mailboxes that you have in your offices, or the cubbies that preschoolers have to store their things. So to understand how memory works in a machine, two examples you can think about is mailboxes in offices or cubbies in preschoolers, cubbies that preschoolers use to store their things. If you need to leave something for one of the other kids, you can put it inside the box. Okay. So if there are a bunch of, I think there is a nice illustration about the boxes there that this article is talking about. Say I want to leave something for someone else, so I store it in one of the slots. So it looks like this cartoon is storing a thank you letter for someone else. So they put it in, let's say if they put it in 14, if it's a student mailbox of some kind, student 14 will be able to look at their box and take it from that box. So you're sending a message to someone else using the boxes. Next to each one of these boxes, you have a number, which is the memory address. So each of the boxes has a number, which is nothing but, if you look at it from a memory perspective, it's nothing but the address of the memory. If I put it in the slot 14, the memory address for my message is in slot 14. That's how you tell someone where to find the thing you've left for them. So if I leave my letter, in this case in slot 14, then I can tell, hey John, I have something for you in slot 14. Each of these boxes is the same size and can hold a certain amount of info. So each of these boxes is the same size and can hold. So if you look at each box, I mean, it is of equal size and it can hold only so many things. The size of the box is specific to the machine. The size of the box is specific to the machine. So different in the older machines, the size of the box used to be smaller. So memory addresses in a 32-bit address space used to be smaller. In 64-bit, I think they are much bigger. That size is called word size. It's usually something like 32 bits or 64 bits. So the amount of information that, the size, that's basically the size of the slot in computer terminology is called the word size. It's usually something like 32 bits or 64 bits. So you can, in each slot, you can store 32 bits of information or 64 bits of information. Nowadays, most OSs are 64 bits, like desktop OSs. Operating systems are 64 bits. So I'm guessing each memory slot will be of 64 bits. So it can store 64 bits of information. But to make it easier to show, I'm going to use a word size of 8 bits. So at least for this article, 8 bits were used. So that means it's easier to represent 8 bits than 64 bits. So each box is further divided into 8 sections. If I count the sub boxes within the big box, I can see 1, 2, 3, 4, 5, 6, 7, 8. So the word size here is 8 bits. If we wanted to put the number 2 in one of these boxes, we could do it easily. Numbers are easy to represent in binary. So if we want to put number 2 in it, we can do it easily. So, because numbers can be represented in binary format. So as you can see, binary format of number 2 is 000010. If you want something that's not a number though, like letter H, so you're saying the binary format of number 2 is 00000010. But something like a letter like uppercase H in this case, we need to have a way to represent it as a number. To do that, we need an encoding, something like UTF-8. So to put a number, we need to if we want to store letter H in this 8-bit memory slot, we need to encode that letter H to a number. And to encode it, we use something like UTF-8. And we need something to turn it into that number, like an encoding ring that we can store it, and then we can store it. Sorry. So to convert that letter to a number, we need an encoder like UTF-8. So we could use an encoder ring, and then we can store it. To convert it, you can use an encoder ring, and then the converted one can be stored. So in this case, a simple dial is being used. And let's say the encoder is saying, hey, H can be represented with number 72. So we store number 72. So the encoder is saying, hey, according to me, H, using my encoder ring, I converted H to a number and it's 72. So we know that we can easily store numbers. Numbers can be converted to binary format and they can easily be stored. So that's what we are doing. So the H has been converted to number 72, and that's what is being stored in this 8-bit at this 8-bit memory address. So when we want to get it back out of the box, we'd have to put it through a decoder to translate it back to H. So there is an encoder that converts, say, an uppercase H to 72. So when we get it back, we get back a number. Now we need to convert the number back to a letter. So for the reverse process, we use a decoder. Automatic memory management. So the next section is called automatic memory management. Let's summarize what we learned in this first section. This first section. So before we understand, so looks like the new JavaScript features called array and shared buffer were needed to understand why array buffer and shared array buffer are needed in JavaScript. We need to understand memory management better. So to understand memory management better at a high level, we need to understand the basics of how memory works. In memory in any system is nothing but a system of memory is divided into slots which are of equal size. In a 32-bit system, each slot is of size 32 bits, which is also referred to as a word. So every memory slot can be considered as a word, and word can be 32-bit or 64-bit. For easier understanding, 8-bit word was used. And to store something in this 8-bit word, we have to, let's say we want to store a number in this 8-bit word. It can be converted to binary format. And one of the examples that was given is number 2. Number 2 was converted to the binary representation of 00000010, and it was stored in this 8-bit word. Same way, if you want to store H, we can't store letter H as a number, so it has to be encoded. We can use an encoder like UTF-8 to encode it. They gave an example of an encoder ring. Let's say the letter H is converted to number 72 by the encoder. We know how to store numbers in a word. Numbers can be converted to binary and stored. So that's what that's what was done. But when we get it back from the memory address, we get back a number now. So we need to decode it. So we have to use a decoder to decode it from number back to a letter, is what they're saying. The next section is automatic memory management. So when you're working in JavaScript, you don't actually need to think about this memory. It's abstracted away from you. Yeah, we don't write any low-level memory code. It's always abstracted from you. This means you don't touch the memory directly. We never touch the memory directly. We understand that. Instead, the JavaScript engine acts as an intermediary. It manages the memory for you. Yeah, so whenever we say, hey, I want to create a variable, blah, 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 JavaScript engine interprets that and allocates a slot for it. If you initialize it, it will store that value at a particular address. So let's say some JS code like React wants to create a variable. Okay. So they're giving an example of JavaScript code that wants to create a variable. So the rightmost stickman with a React, head, wants to create a variable called greeting and set it to hello. So this is interpreted by the JavaScript engine. I think the gatekeeper here, the person with the cap, is the JavaScript engine, and that will interpret this and store it in memory. So what the JS engine does is run that value through an encoder to get the binary representation of the value. So it takes hello and HELLO. So if you see, the topmost one is H, the second one is E, the third one is L, the fourth one is also L, and the fifth one is O. So JavaScript and engine is encoding the string, each character in the string, and then it's storing the encoded values in memory. And it will find space in memory that it can put the binary representation into. This process is called allocating memory. So JavaScript memory takes care, if your app is saying, hey, I want to create a variable and assign it a value of hello. So JavaScript engine takes that, decodes it, allocates the memory, and puts the value in memory. Now, this process is called allocating memory. Then the engine will keep track of whether or not this variable is still accessible from anywhere in the program. If the variable can no longer be reached, the memory is going to be reclaimed so that the JavaScript engine can put new values there. So the JavaScript engine keeps track of this variable. JavaScript engine keeps track of this variable and sees if it's is being used by the JavaScript code anywhere else. If no one is using it, then it will reclaim it, and it will the memory that's available will be used to store other values in it. This process of watching the variables, strings, objects, and other kinds of values that go in memory and clearing them out when they can't be reached anymore is called garbage collection. So this process of watching the variable, JavaScript engine is watching the variables and saying, hey, if no one is using it, it's going to reclaim it. That available space will be used for other variables, storing other variables and the values for it. This process is called garbage collection. Languages like JavaScript, where the code doesn't deal with memory directly, are called memory managed languages. So languages like JavaScript, where the code doesn't deal with memory directly, like if you take the C language, in C language, when you write code, you do memory allocation yourself. And then you are responsible, the app in this case is responsible for freeing up that memory. So let's say you create a variable in the C language. Let's say you create a character array, you allocate memory using malloc, and then you are responsible for deleting that memory at a later time whenever it's not being used anymore. But in languages like JavaScript, JavaScript engine will take care of it. You just say that, hey, I want a variable called X and I want to assign it hello. JavaScript engine will take care of allocating the memory, decoding it, and then putting the binary values into this allocated space. And the JavaScript engine will make sure as soon as this variable is not being used anymore, it will free it up. That's called garbage collection, and these kind of languages are called memory managed languages. So this automatic memory management can make things easier for developers. So they're saying this automatic memory management can make things easier for developers, but it also adds some overhead, and that overhead can sometimes make performance unpredictable. Yeah, so basically garbage collection can happen anytime. Garbage collection, when it happens at a time when you're, let's say, the UI is being refreshed or something like that, then it will take up some CPU time. So it could end up having a performance impact on your app. So it could, if memory management happens at undesirable times, then it'll impact the performance or the perceived performance of your app. And it will become unpredictable. So anyway, to summarize this section of automatic memory management, JavaScript at a high level does the memory allocation, and it is considered it allocates memory itself, it decodes. The JavaScript engine will take care of memory management for you. You declare a variable, it creates, it decodes it, stores the binary representation, and as soon as the JavaScript engine, as soon as it finds that this variable is not used anymore, it will free up the memory. That is called garbage collection. And these languages, like JavaScript languages, are called memory managed languages because they manage memory themselves. There are downsides to it. Performance can become unpredictable, is the summary of automatic memory management. Manual memory management. Languages with manually managed memory are different. For example, let's look at how React would work with memory if it were written in C, which would be possible now with WebAssembly. Okay. C doesn't have that layer of abstraction that JavaScript does on the memory. Instead, you're operating directly on memory. You can load things from memory and you can store things to memory. So they're giving an example. They're saying if React were written in C, so which would be possible now with WebAssembly. WebAssembly, I think you can now, the new standard, a new standard called WebAssembly. All major browser vendors are adopting the WebAssembly standard. WebAssembly standard is a binary format. You could create a WebAssembly module using any language. But that's kind of a little digression, I guess. But let's say what they're saying is if you use C to, C doesn't have a layer of abstraction like JavaScript on memory. So as I talked about earlier, in C, you can allocate memory in your app yourself, and then you are responsible for deleting it also. So it looks like this is they're saying this is WebAssembly, a React app that's developed in WebAssembly. And this one is directly storing values in memory and retrieving it directly from memory. There is no JavaScript engine in between this WebAssembly app and the memory. So when you're compiling C or other languages down to WebAssembly, the tool that you use will add in some helper code to your WebAssembly. For example, it would add code that does the encoding and decoding bytes. So when you're compiling C or other languages down to WebAssembly, the tool that you use will add in some helper code to your WebAssembly. For example, it would add code that does the encoding and decoding bytes. The code is called a runtime environment. The runtime environment will help handle some of the stuff that the JS engine does for JS. Okay. So even for WebAssembly, there is a runtime environment that will handle some of the stuff that the JS engine does for JavaScript. Even for WebAssembly, there is a runtime environment. But for manually managed language, that runtime won't include garbage collection. So if you manually manage a runtime, for a manually managed language, that runtime won't include garbage collection. So like for a language like C, because it's manually managed, that runtime will not do garbage collection for you. If you write code that compiles to WebAssembly, looks like you'll have to write your own memory management routines. That means if you allocate memory to store a variable, to store some data in memory, you have to write code to unallocate that memory also. This doesn't mean you're totally on your own. Even in languages with manual memory management, you'll usually get some help from the language runtime. Okay, they're saying even in languages with manual memory management. So like C language, even though it is you have to manage memory manually yourself in the code, there is some help. For example, in C, the runtime will keep track of which memory addresses are open in something called a free list. So even in C, the runtime will keep track of which memory addresses are open in something called a free list. So even in C language, the runtime will tell us what are all the memory addresses are available for us to store data into. This is what I'm getting from this. So this is the free list. Basically, if you see 1, 2, so the slot 1 and 2 are empty, and then slot 8 through 15 are empty, and 19 to 21 are empty. So that looks like the runtime maintains a free list of the memory addresses that are available. So you can use the function. You can use the function malloc, short for memory allocate, to ask runtime to find some addresses that can fit your data. So in C language, we can use a function called malloc that will return me, let's say I want to allocate 5 bytes. It will return me a memory address where I can store these 5 bytes. A function like malloc will do that. This will take those addresses of the free list. Yeah. So if malloc returns me a reference to an address, then it will take those. Whatever it allocated, it will take those slots out of the free list. When you're done with that data, you have to call free to deallocate the memory. So in C, you have to call another method called free to deallocate the memory. Then those addresses will be added back to the free list. You have to figure out when to call those functions. That's why it's called manual memory management. You manage the memory yourself. So in a language like C, if you do a malloc to allocate memory, then you have to decide when to call free. As a developer, figuring out when to clear out different parts of memory can be hard. If you do it at the wrong time, it can cause bugs and even lead to security holes. If you do not do it, you run out of memory. So as a developer, it's tricky. I mean, disciplined developers always know when to call free, but if you don't call free, or if you call free sooner than, if you call it ahead of time, then basically there will be a lot of problems. It will cause bugs and security holes. This is why modern languages use automatic memory management to avoid human error. But that comes at the cost of performance. I'll explain more about this in the next article. Looks like in the next article, Lin will explain what are the problems what are the cons. I mean, there are obviously advantages of automatic memory management. It will reduce the number of bugs in your code because the JavaScript engine, in this case, will take care of unallocating the memory and then reusing the space for storing other things in it. But there is a downside to it. Looks like they will talk about the downside in the next article. Anyway, coming back to summarize this section of it, manual memory management is used in languages like C. The app. So if you use C and if you want to allocate memory, you use a function like malloc, and you are responsible for freeing it up. The downside of you allocating the memory and freeing it is if you forget to unallocate the memory, then you'll run out of memory. And if you unallocate the memory using the function free before ahead of time, then you might cause other problems. Like basically, you won't be able to access the address. At a high level, manual memory, that's the manual memory management section of it. If I want to summarize the whole thing, the gist of it is to understand why array buffer and shared array buffer were introduced in JavaScript. We need to understand memory management properly. Memory management, JavaScript languages like JavaScript use automatic memory management. There are downsides to it. The JavaScript engine takes care of memory management in JavaScript. In the other side of automatic memory management is manual memory management. Languages like C give you the ability to manually manage memory. Examples of manual memory management using C is use malloc to allocate memory and free to unallocate memory. The downside of it is you might introduce bugs if you unallocate memory before I think if you allocate memory and don't unallocate memory, it'll cause memory leak. But on the other side of it, if you unallocate memory and then end up using the variable, then it could cause like an exception and crash the application. In the next article, Lin will talk about what are the disadvantages of automatic memory. So I think one of the things about automatic memory management is it comes at the cost of performance, and the next article will explain more of that. So the next article is this, a cartoon intro to array buffers and shared array buffers. I will stop this video and I will talk about I'll talk about this topic in the next video. Thank you.